Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Cyber-Physical Systems, ISC. Today's talk is by Professor Siddhartha Banerjee, and he'll be speaking on constant regret algorithms for online decision-making. Sid Banerjee is an associate professor in the School of Operations Research at Cornell, working on topics at the intersection of data-driven decision-making, network algorithms, and market design. His research is supported by grants from the NSF, including an NSF Career Award, the ARL Network Sciences Division, and Engaged Cornell. He received his PhD from the ECE department at UT Austin and was a postdoctoral researcher in the Social Algorithms Lab at Stanford. He has also served as a technical consultant with the Research Science Group at Lyft from 2014 to 2018. Before we move on to the talk, we'd like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Professor Siddhartha or type them in the chat box and we'll moderate it with him. Over to you, Professor Siddhartha.
Thank you. Thank you very much for the invitation. It's been a long time since I've been back. I don't know if any of you were around, so I think I last visited ISC back in 2015. So I also realized this is an odd time for many of you for the talk, so I'm glad you could accommodate it at this time. It's somewhat early for me, so in case I forget things or get confused, which is not unlikely given I'm just getting my coffee right now, please stop me, just interrupt as much as you want. Some of you may have seen parts of this talk before, in which case interrupt me even more. I have a fair bit of material. I don't actually need to go through all of it, so just stop me anytime. I can also see all of you, Stasha. I can see your avatars and or monitor the chat since I'm using a separate screen. So feel free to turn on your computers if you also feel like, and like if you're confused and make disapproving faces, then I can figure out what's going on. Okay, so I'm gonna jump straight in. So I'm planning to talk about constant regret algorithms for online decision making, and it'll take me a little while to sort of build up to what exactly I mean by this, and what I'm hoping to give you are a bunch of examples of what exactly we've been doing in this space, and then give you this one general way of thinking about a lot of these problems. Now, kick off with a puzzle just so that we're all situated on the same place, and so that I also get some of y'all involved in talking about these things. So this is the puzzle that I want you all to think about. So this is a very basic problem in online decision making. It's sometimes called the online unit demand knapsack. The idea is that you have a collection of rewards which are arriving over time. So you have these t values which arrive over time. You don't know what these rewards are upfront, but when the tth reward arrives, you actually see it. So at time t, you see the reward vt, and vt, but till then you don't know what these vts are. And out of these t rewards, you have to select some k of them. So that's why I'm calling it a unit demand knapsack. The idea is that you have a knapsack of capacity k, and each of these rewards have size 1. So what you need to do is, as these rewards come in one at a time, you need to make a selection, and as soon as you select it, that gets added to your knapsack, and your aim is to maximize the total sum of rewards. Sorry. Okay, so I haven't yet, like many of you would have seen problems that look like this in various courses and various things that you do. And you may have noticed that there's something a little odd in the way I'm formulating it right now. I haven't yet told you what the reward distribution is or like anything about the rewards. And so here is the piece of information that I'm giving you, which is that I somehow know that all of the values, all of these VTs are numbers, are either the number 50 or 100. So again, just to explain the question again, I'm getting these rewards V1, V2, etc. up to VT. I don't see the rewards before they come in. Only when they come in, I see it. But I know at each time that this number is going to be either 50 or 100. So maybe the first number gets revealed and I see it's 50. Then the next one is revealed, it's 100, and so on and so forth. And as soon as I see the number, I need to decide whether I accept it or not. And the rule is I can only accept K. I'm hoping some of you all know my good friend Aditya Gopalan, who was a batchmate of mine in grad school, and being sort of senior to me, he was usually always smarter about these things. And so the way I'm setting up the problem is I'm saying that Aditya actually knows exactly what all the values are before me, but I have no idea what the
Sorry to interrupt here. I
Parimal,
think
yeah, I see
Parimal
Parimal's
has a
hand. So
question.
yeah, you have a question. Or are you giving the answer?
Sorry, I what I didn't get is that what is the action here? Select
Right.
K.
So the action is you either accept or reject. So you see the value. So
these VTs are randomly being selected, which is through some given distribution you cannot control. You can just accept.
I'm not saying anything about it. I'm not even saying they may be arbitrary, they may be adversarial.
Okay, but you just get to say I keep it or reject it. That's it.
Exactly. So the only information that you have is that the numbers are either 50 or 100. So right now you've seen 50 and 100. Maybe you've accepted the 100, you've rejected the 50.
If you just talk about Sidhu, so it seems like I would always reject all 50s, right? Whenever I see 100, I accept, and whenever I see 50, I reject, right?
Good, but that may not be optimal.
No, I'm saying, like, is there something, some other constraint which I'm missing? Why would you not just reject all 50s?
What if all the values are 50?
Okay, then okay. So I thought that I had information that there is some. Okay, you're right. That's a good point. But if I knew that there's 100 possible, then I will do it, right? You're right. If I don't know that there are 50 and 100, because you told me it could be 50 and 100, right?
Yeah. So all I'm telling you is that the numbers can be 50 or 100, but it's possible all the numbers are 50.
Hey Sid, won't I just like accept hundreds and once so I know capital T? So like at the end when only.
Okay, I think Sid kind of knows the answer. Well, okay, the other Sid. Sorry, can I call you Sid still?
Yeah, they still do. Yeah. So
you have got the answer. But
okay,
you're right. I know capital T.
So I mean, I just wait till the end and then I select whatever the last. Like so, I keep look. So earlier I'm greedy, as Parimal was saying. I select hundreds.
Yeah.
But at the end, let's say I have K prime slots left, and if there are only K prime values also left, then I select all of them.
Okay, awesome. So for everyone else, I feel, aren't you supposed to let your students answer? But no, I'm joking.
Okay.
For everyone else, did you get what?
If I can interrupt. So I just wanted to understand.
Yeah, go ahead.
You want to select K. So I missed this. What is K here?
K is the number which is given to you up front. So maybe think of, So maybe think of this as 100, or I shouldn't reuse 100. So maybe there are 200 rewards out of which you want to select. You have space for only taking 70. So Sid actually kind of gave the answer, but for those of you who didn't figure out what he said, Sid's claiming I can do exactly as well as Aditya despite not knowing any of these numbers beforehand. So Aditya knows all the numbers. He's picking the best he can with full information. And the scheme that Sid gave is actually getting exactly the same as what he gets without knowing this information. And the scheme that Sid is suggesting is initially, whenever you see a 50, just reject it. When you see 100, just accept it. This keeps going on. You see a bunch of 50s, keep rejecting. But at some time, what's going to happen is that the remaining time is equal to the budget you have. So you've reached a certain point and you have some budget BT, and the time remaining is T. But if these two are equal, at this point, you should just accept everything. It doesn't matter what else is coming, because the point is up to now, you've only accepted the hundreds. And from this point onward, you accept everything. And the claim is this is optimal. Any questions about this? Is this obvious? Or okay, so let me tell you why do I even start off with this puzzle? Whenever I give this puzzle, for a lot of people who are more like experts in thinking about things like bandits and online decision making and regret and things like that, they almost always get confused. They sort of look at this and say, yes, there's an algorithm, you use no regret, you get the square root t regret, etc., etc. Whereas there was a very simple process to just get almost exactly the optimal, in this case, exactly the optimal in hindsight. So there's something weird about the information structure here, which is making this problem extremely easy, even though you don't have the information. Any questions, thoughts about this? Is it clear to people that I can do exactly, I can get the optimal solution? Maybe I'll wait for like a few thumbs up for.
Oh,
Is it something?
Yeah, I think what is interesting, I feel that you still have some information, even for the person without full information, right? That is the alphabet size in some sense.
So I have the alphabet size, and as Sid was pointing out, I also know the horizon.
Right. Okay.
But that's still interesting, right? Like, why is it? It at least wasn't obvious to me a priori that those two pieces of information actually give you enough. Any other questions? Like,
is it something similar to?
Sense?
Sorry. Online knapsack problem? Is it something similar to that?
The online knapsack. Yeah, I mean, technically, this is the online unit demand knapsack, except if you see the online knapsack, people will say things like, oh, you either get a competitive ratio or you get some kind of regret guarantee, whereas here we are saying we are just optimal.
I see. So it's sort of stabilizing some sort of regret, like max weight scheduler. Is it like a one-dimensional knapsack, or is it?
It is a one-dimensional knapsack. Okay. I will generalize it to other things. So it's good that you're now starting to think a bit about why exactly this worked out. So maybe one more point I'll emphasize. So this particular policy that Sid came up with, this idea of finding this time over here, that's kind of a very special type of policy. So in the sort of formal lingo, this is the stopping time. So this is the point which is you're going along the process, and based on the actual sample path, there's a particular time which you can identify, the time when your current budget is equal to the remaining horizon. And in some sense, like the way this policy has been constructed is to carefully define the stopping time. I mean, it may seem trivial at the moment, and okay, this is kind of trivial, but it's very different from anything else or most other policies you would have seen. Like it's not, it kind of is a stationary policy, but it's got a very particular structure. And this is going to come up multiple times throughout this talk. So okay, maybe let me not sort of beat this dead horse anymore. So what do I want to talk about? What I want to talk about is this phenomena that when you have these online decision-making problems, often they are going to get much more complicated. Hopefully, very soon you'll agree with me that the problems are not as trivial as this one over here. But it still turns out that in many of these problems, even if you don't have information about arrivals, you can do almost as well as the hindsight problem. And when I say almost as well, you're not going to, in this case, your regret was 0. What we'll show is that, or what I'll try to convince you is that for many problems, you won't get a 0 regret, but you'll get a regret which is a constant. It's some number which is independent of t and it's independent of k, which are kind of the parameters of this problem. It'll depend on the distribution. It'll depend on some other features of the problem. So it'll depend on some notion of the complexity of the problem, but not on the natural parameters of the problem. So that's what I want to talk about. Like I want to give some examples of this phenomena and try to make it more and more complex to try and give you a feeling of what's going on. And then I'll try to generalize this idea that we are looking for certain stopping times and we are using the stopping time to argue that we do very well. And I'll try to talk about this general way of analyzing these processes using a certain sample path coupling. So that's the plan. And then I'll maybe take some time to explain how it fits in the larger picture of online decision making. Okay, and this is work that I did with a bunch of collaborators. So most of it was done with my previous PhD student, Alberto Vera, who, so he's now graduated. Daniel Freund was also a collaborator of mine at Cornell, but he's now a faculty at MIT. And then Itai Gorovich was a colleague of mine who's now moved to Northwestern. And these are some of the references. If you go to my website, all of these papers are available. Okay, so let me now make life a little more complicated. So here is the more general version of the problem which I think Rahul was asking about. So here is online packing, but now compared to the knapsack, I'm no longer assuming it's one dimensional. So I have multiple different budget resources. So this is a resource with budget B1. This is a resource with budget B2. I may have these such resources. And each arrival is now asking for a vector of resources. So it's asking for some vector AI, which is some, let's think of it as some point in 0, 1 to the D. So it's asking for some set of resources and not for the others. So one example that people often give is think of these as seats on different airplanes, and you're trying to get a connecting flight to go somewhere. So you want to seat on both the first flight and the second flight. And some other people only want it on the first flight, etc., etc. And each person also has a value VI, which is, and the type of the person is sort of both this resource requirement and the value. And now, unlike before, I will need some stochastic assumption. So what I'm going to assume is that each agent has some type theta I, and this is with probability pi of t. So these probabilities need not be these need not be sort of time invariant. It could change over time, and you'll see later like what all we can admit. But we know these probabilities. So we have some historical data. We can figure out what these probabilities are. And what we want to do is we want to sort of use in this problem as time goes on. I want to allocate these resources so as to maximize the sum of the rewards collected while satisfying the budget requirements. Any questions about this? So this is kind of the first example I'll talk about. This is sometimes called, it's either called online resource allocation or online packing. In operations research, for historical reasons, this is called network revenue management, but it's this basic process, the same problem. And just as an aside, the parameters of this problem are each of these, the budgets and time. So in particular, the state space, the size of the state space is at each time you need to keep track of each of these budgets. So the size of the state space is the product of all of these. So it's T cross times B1 times B2. Oh, I'm using a superscript, sorry, etc. So you can try to solve this optimally, but it's typically going to be way too large to actually do that. Yeah, but
even the offline problem, won't that be like NP, like computationally hard?
Yeah, up to, so yes, but I'm going to sort of assume we are in a regime where the values are bounded. So
okay.
I don't want to solve it exactly, but I'm willing to take so the loss, if you do just the naive rounding, would be constant. Yeah, but that's a good point. This would be an integer program.
Yeah.
Yeah. Parimal, is your hand still up? Or?
Yeah, sorry, Siddharth. So I was trying to understand how is this problem similar to the first problem? Like, just if you can tell me the budget was that, and the AI was.
Yes, in the first problem, the budget was K. The D was equal to 1. There was just one resource. The budget was K, and each of the AIs were 1.
I see. Okay, and VI was 50 or 100.
And VI was 50 or 100. Now I'm assuming VI is some number drawn from a distribution.
Okay, thank you.
It's VI with probability pi of t. No, great, thanks. Yeah, any other question? Like, I want to make sure these settings are clear. I'm stating them somewhat abstractly so that you can try and fit them to your chosen application, but then I want to sort of give you a unified result for these. Okay, so that's setting 1. Here's setting 2. This is sometimes called the generalized assignment problem, but let me give you an actual example that we worked on. So many like online platforms. So I did some work with Lyft, and but like most like online companies, what they use is they get their payments processed by different companies. So in the US, there are these two companies, Stripe and Square, which are essentially clearinghouses for all your credit card payments. And each of them have different processing fees, but they actually have different processing structures. So what happened with the company we were working for is they were using 2 processing firms. One of them used a fixed fee per transaction. So if your transaction was like 100 rupees, it would charge like say 2%. So you'd always pay two rupees to this processing firm for every 100 rupees transaction. So you have 200 rupees, 4 rupees, etc. Whereas the other firm just charged, sorry, that was firm 2, which charged a percentage, whereas firm 1 always charged a fixed fee. So it was always 5 rupees no matter what's the size of the transaction. And if you think about it, the obvious thing to do is whenever you have big transactions, send it to firm 1, and small transactions, you should send to firm 2. Except that firm 2 also put a requirement. I mean, they knew that they were charging this percentage, and so they would only get small amounts of the small transactions, but they put a requirement saying you have to meet a minimum average transaction size at the end of the month. Otherwise, there's a penalty. So if at the end of the month, your average transaction size is less than like 100 rupees, then you need to pay a penalty for how far away you are from that average. And these companies have very different transaction sizes. I mean, you think of a ride-sharing company like Uber or Ola, like some rides are cheap, some rides are expensive, but they have some statistics about how these rides are. And what they wanted to do was figure out for every transaction that's coming in, should I send it to firm 1 or firm 2? With this knowledge that for firm 2, the average transaction size at the end of the month matters. So it's a wordy way of describing like the general framework for these sort of problems are what's called the generalized assignment problem. And this is kind of an online version of it. I want to route the payments in so as to minimize the costs. So again, I know the distribution of each payment. So at each time I get some payment coming in with some probability PI, it has value VI, and I need to decide which one to route it to. Okay, here's an example which I promised in the abstract. So this is online bin packing. I'm giving it more of a cloud computing spin for this. So you have a cloud provider, you have these virtual machines with different resources, and these resources could actually be vectors. So these could be memory and processing power or something of that sort. And then every arriving job has some minimum resource requirements. It has a vector of requirements which says, I need so much memory and I need so much CPU, etc., or so many cores, whatever you have. And what you can do is you can take these jobs and load them onto existing machines which have enough available resources, or you can start a new job, a new machine to fit this. But once you load these jobs take long time. So like the time scale is the jobs last for a long time, they're not disappearing. So once you load a job, you can't remove it. You can't sort of stop it and move it around. And you have a stochastic arrival process of these job sizes, and the question is, how do you route them to minimize the number of machines that you start? So like the picture I want you to have in mind is something like you have these machines, each of them are maybe a fixed size. I'm drawing it as a square to say there are 2 resources. And then this job comes in, you take it, you fit it over here. The next job comes in, it looks like this. You maybe manage to fit it over here. Then the next job is really big and you're like, okay, I have to start a new machine and fit it over here. And then so on and so forth. Does this make sense? And what you know is for each of these jobs, you know the resource requirement BT, but you only know it when it arrives, and you know that this is drawn from some distribution P of T. Questions about this? So these jobs are coming in, and my aim is to try and sort of fit all of them while minimizing the number of machines I start up. So think of it as loading jobs at the beginning of the day, and then they're processing.
So sorry, so just to, again, trying to
Yeah.
relate this to your abstract setting, what is the value here? Budget is sort of clear, and AI is also clear.
Right. Yeah, so this is why I'm sort of making it a little more abstract. So here I really care about the cost. So I care about the number of machines I start. Like at the end of the day, at this point, the cost is 2 because I started machine 1 and 2.
I see. So here you would just want to keep least number of machines on.
Exactly. So at this point, I mean, and that's a really good question, because some of you must be thinking, what the hell is common between these? I mean, yes, these are online problems, but just like mathematically, like is there anything common in the structure of these problems? Like, why am I grouping them together? So I claim there is something common. So in particular, there's sort of 3 important features which are happening in all of these problems. So the first one is that the randomness is exogenous. So what I mean by that is all the arrival process doesn't actually care about the state of your system. So a person who's arriving with some offering to pay a certain price and wanting some resources doesn't actually care yet about like how many resources you've sold. As long as you have enough capacity, that person is happy as if you're willing to allocate. Or these virtual machines, or sorry, these jobs coming to the cloud cluster doesn't care about what jobs have come in the past. So there's some arrival. Okay, yeah. So Molly's asking, are there infinite VMs here? Yes. So I have infinite VMs, but I want to start as few as possible. I could always start number of virtual machines equal to number of jobs, but that's way too large. I want to pack them in as much. You can't block an arrival. You have to serve it. Yeah, you can change that around, but I'm assuming you have to serve everything. Okay, so that was the first feature. All the randomness is exogenous. What's a little more interesting is the second bullet point, where I'm saying that all the actions are exchangeable. So what do I mean by that? In all of these problems, at the end of the horizon, if I told you how many times for each arrival type I took a certain action, you can compute the net function, the net reward or the net cost. So in the VM case, if I told you for each arrival type how many times I mapped it to a certain configuration. So this is the configuration of jobs over here. I have one horizontal job and one vertical job. And here I just have one big job. So if I tell you how many for each arriving job, which configuration I mapped it to, you can sort of do like a jigsaw puzzle in reverse and calculate how many virtual machines I actually used. Or if I tell you how many arrivals of type theta I allocated, you can check that it satisfies the budget requirements and then see the total value that you've earned. I don't actually care when I took the action. I just care about the number of actions I took for each type. And I'm defining action a little vaguely, but you can try and convince yourself that the only thing which matters are the aggregates, but not the sequence of actions. So this is very different from if any of you think about, say, queuing problems, where the sequence really matters. In these problems, the sequence didn't matter. And the other thing that I'm assuming is that in each case, I don't know what the arrivals are, but I have some statistical information. So in the general case, maybe I just know the distribution from which these arrivals are generated, but I don't know the arrival. So essentially, there's some regularity in the process, and I'm aware of this regularity. And maybe you can make an argument that this is something I learned from historical data. And it doesn't need to be IID. It could be time varying. It could be periodic or something strange like that. But I know what this process is. Okay, so here's the sort of short summary of what I'm going to present in the remaining half an hour. So what I'll show you is that as long as the set of types is finite.
Hey, Sid, sorry, yeah, quick question. Can you speak to the second point for, in particular for this bin packing problem? Because there, it's not obvious to me that like you can pick, say, a bunch of small jobs, open a bunch of, like the order might influence the number of machines you open, right? Or like
the order might influence the number of machines. That's correct. What I'm stating is at the end of time, if I tell you all the actions I took, so an action is now what's called a configuration. So I'm basically saying this is the configuration of jobs. So something that looks like this is a configuration, and maybe like this. That's one configuration. Okay. Here's another configuration. I'm telling you for every job of each type, which configuration I mapped it to.
Correct. Okay. So it's not the types of jobs that it's a bit more richer than that.
Yeah, so the action space is richer. So the state is the type of the jobs, the action is the configuration that you map the job to. So it is subtle that this is exchangeable, but it is exchangeable.
Okay.
Yeah, no, that's a great question. Yeah, I mean, this wasn't actually obvious to us when we started off.
Okay. Yeah, thanks.
But again, so what I want to show is that for all of these processes, as long as you have a finite set of types and what I'm calling a natural arrival process. So what I mean by that is that someone fixes the distribution first over these types, and then we make the problem bigger and bigger. We scale the problem. If this seems weird, just think of it as you have any distribution over these IID types, and the distribution doesn't depend on T or any parameter of the problem. What I'll show you is that in all of these cases, there is a very simple policy which has regret, which is independent of the horizon, and it's independent of all these budgets, the state space of the problem. compared to the optimal solution with full information. So the optimal solution in hindsight, you can get arbitrarily close to that using a certain policy. There's the question, are the jobs leaving in the VM case? So I'm assuming the jobs are not leaving. So if the jobs left, then this exchangeability breaks down, because we need to know which job was admitted before or after which job left. And there are extensions of this to things where, but yeah, in this talk, I'm not talking about that. Okay, so that's what I want to talk about, which is how do we actually get these kind of uniform regret. Now, you may think this is some theoretical tool, so let me convince you that it's not just theoretical. This is genuinely infinite, like uniform regret. But first, let me actually give you a sense of what this algorithm looks like. So all of these processes that I talked about, given that I know the distribution of the arrivals, these are all what are called Markov decision processes. So these are sort of finite horizon control problems where I can write down the optimal solution. So the optimal solution, you can sort of compute it using dynamic programming. You go till the end, you work backward, you say, if this is my state of the system, if some arrival comes in, if I accept, there's some probability something happens, if I reject, etc., etc. And of course, what people don't like about DP is, well, firstly, you need to know the exact distributions. That's not that critical, but I mean, that's true. But what's a little more tricky is that the size of the DP grows with the size of the state space. So this is what's called the curse of dimensionality. So for example, for online packing, your problem size is T cross B1 cross B2 up to BT. We can agree, we can debate whether this is small or large, but typically this is very large. You don't want to solve a problem with that complexity. So in order to get around this is a very common idea, and I mean, this is an idea used across like control, computer science, and in all sorts of fields, which is, instead of looking at the optimal policy, can I come up with some other benchmark policy? So some other policy which is better than the optimal and try to compare against that. And the simplest one to think about here is what I had in my example earlier with Aditya, which is that maybe somebody, like, what if the benchmark knows the full arrival process, and then it is just solving some kind of optimization problem in order to decide what the solution is. As Sid was correctly pointing out, the actual optimization problem should be an integer program, but what I've written here is, well, I haven't exactly specified whether it's an integer program or not, but like it actually turns out you can even just take the linear programming relaxation. The gap between the two is small as long as these VIs are not, as long as these VIs are bounded. I don't need the integrality assumption. I only lose a constant. And the object I'm interested in is this notion of the regret, which is the gap between this problem in hindsight. So note that this benchmark itself is random. It depends on the actual arrivals, which I don't know when I'm solving the problem, but I could calculate it at the end of the day, and that gives me some random variable, V offline. And I want to see how well I do compared to that. And I want to take expectation over every sample path. And that's what I'm defining as my regret. So it's literally at the end of the day, I'm looking at what's the best I could have done. Yeah, go ahead. There's a question.
Sorry, Sandhya.
Yeah, I think Sandhya was first, so go ahead. Hi, Sandhya. Sorry, you're still muted. Parimal, maybe do you want to go first then?
Yeah, sure. So I mean, now I'm lost. What is there were D-dimensional here, right? But now I'm seeing your budget is only B. So
this is a vector equation. So these are all in R2.
Oh, I see. For each of those.
Yeah.
Okay.
Yeah, this
Thanks.
is AI transpose X. Yeah.
Got it. Thanks.
Yeah, Sandhya. I don't know if you can. If your audio is, you're still muted though. Okay, maybe in the interest of time, I'll keep continuing, but maybe you can type your question. I'm happy to get back to it. But any other doubts about what the regret is? The regret is, if the formalism doesn't make sense, just think of it as I give you full information and I ask you to solve this in hindsight, and you're comparing to that solution. Okay. Sorry, Parimal, you had another question or?
No, sorry, I should lower my hand, but I was just thinking that so algorithm would basically know the observation until whatever has happened to us. So at every time I
Exactly.
see the whole, the history. Right? Yeah, okay. And
Yeah,
that's
so the
based on that I'm
algorithm
going
has
to
to be
take
what's
this
called
t plus one.
Yeah, perfect. So the algorithm
Okay.
should be non-anticipatory, but my benchmark can know the future.
Thanks.
Okay.
So you're not
here's
assuming any scaling, huh? As in,
I'm not assuming any scaling.
this will make life difficult for you. Like I can just blow up the values by a factor of 100 and your regret goes. So
yeah, so let me show you what the regret expression is, and then we can. So I'm really going to focus on T and B being large, and everything else I'm going to think of as being smaller. But yeah, so I guess in that sense I am assuming T and B are scaling, whereas the others are not. But it's going to be a finite time, finite T, finite B guarantee.
Okay, got it.
Okay, so
sorry,
kind of
one more question.
Yeah, go ahead.
So this is very interesting. I find that so you've written this expectation, right? And this expectation over this exogenous arrival, correct?
Yeah.
Am I audible first of all? Okay, good.
Yeah,
and so it's there's no worse. Right.
Yeah.
Sorry, my question is.
No, so I guess you were asking, is this worst case? So this is definitely not going to be a worst case guarantee. I can hear you. Can you hear me?
Right. So it's really like just nice randomness, right? There's just there's one randomness only, right? Or is there something else I'm missing? It's just the arrivals are random. Correct?
There's just one arrival process. But this could be a complicated arrival process. It could be like a Markov chain or like some weird time varying thing, but it is stochastic.
Right. Okay. Thanks.
Okay. So here's the policy. So the policy is basically, I'm going to state it as a meta theorem first. So imagine instead of like actually solving the problem, imagine someone built some kind of like a prediction oracle. So someone gave you this piece of like machine learning code, which thinks about what the offline is going to do. And then for every arrival, it predicts a probability whether the offline value would decrease or not if you accept that arrival. We're still just talking about online packing. But more generally, if you take a certain action, what's the probability that you regret taking that action in hindsight? Now, if you're worried about how do you construct such a thing, one thing that you can do is you can take, like maybe you can build a simulator to try and compute it. So you take, for every action that you take today, you simulate the future arrivals, and then you check whether that action made sense or not. But you have such a predictor. And a natural thing to do is, in this case, because there's only two actions, accept and reject, I can look at these probabilities that you associate with each action being regretted in hindsight, and then I'll pick whichever is smaller. So if this probability of regret, if you accept, is less than 0.5, or if it's smaller than the probability of regretting if you reject, I just go with that. So I'm basically just going with a greedy policy, which looks at this probability of regretting an action in hindsight and picks the action with the least probability of regret. And I'm calling this a base selector because you can think of it as I'm trying to predict what the hindsight problem is doing. And then using that predictor, I'm trying to match offline. Rahul, you had a question.
You're not allowing for randomized controls or actions over here?
I'm allowing for randomization, but actually one very important principle is randomization is a really bad idea here. I'll show you this in a second, but I am allowed to randomize. But the policy I'm suggesting is not randomized. It's a thresholding policy.
I see. Thanks.
And here's kind of one of our main early theorems, which is that under very mild tail bounds on the number of arrivals of each type in the future, essentially, yeah. So under mild tail bounds on the arrival process, this policy has regret, which is independent of the entire of time and the state space. So compared to the optimal in hindsight, I lose a constant. And actually, let me give you an exact formula for this, or at least an upper bound for this. So that will hopefully somewhat answer Sid's question. So this was like, firstly, how do I construct this predictor? Well, one way of constructing the predictor is you take this LP that we were constructing for the hindsight, and I replace anything which is random with its expected value. So I don't know the number of arrivals of each type coming from now till the future, but I replace the number of arrivals of type I with the expected number of arrivals of type I. And this is something I can do from just looking at the statistics. And then when I have this LP, I sort of resolve this LP every time. I update the budget, I update this expected number of future arrivals, and then I interpret the solution as a probability. So I look at xi of t divided by expected value. This is some number between 0 and 1. I think of this as the probability of accepting, and I accept if it's more than 0.5. And this particular version of the base selector already gets you a regret, which is at most the maximum value times something like the sum of 1 over the probabilities. So this again comes back to Sid's question that yes, if the maximum value is very large, I'm in trouble. But it's kind of clear just looking at this that this is independent of T and B, unless T and B sort of sneak in via the maximum value and the probabilities. And this is part of it's a special case for a much more general phenomena. Now, in case you think that these numbers are not great, like maybe this is very large compared to T, let me actually show you how this does in practice, and I'll come back to this thing. So this is how it looks like in practice. So the green and the red were sort of the best known, okay, there's a little lag, but so the green and the red were the best known policies before what we came up with. It was kind of known for this problem that you should have policies which get square root T regret, and everyone thought square root T was type. And what you see at the bottom is our policy, and we're plotting regret in each case, and you can see the regret is basically just 0, even though I'm making the problem bigger and bigger. Joy, you had a question.
Hey, Sid, what is PI in that expression? Or it's not important?
Not super important, but it's the probability of each type. So I'm assuming it's a finite set of types.
Okay.
And I'm saying, suppose it's IID just for convenience, then this would be the probability for the IID case. So in general, it somehow depends on the minimum probability of each arrival in the future.
Right.
Yeah, no, that's a fair question. It's
like some of these geometric expectations.
Yeah, it's just sum of 1 over. You can think of this as 1 over p min or n over p min. So it depends on the number of types. It depends on the minimum probability, but not on t. Jed, did you have a question?
Yeah. Sorry, I missed this. The pi t, in the definition of pi t, it's the probability that the v offline decreases if offline accepts the tth arrival, but decreases compared to what? Can you just mention?
Yeah, that's a good question. So what I really mean to say is think about what the offline policy is doing with full information, and now force it to take a certain action today and ask it to resolve given the information. So what's the best you can do if I force you to take an action today and then you're optimal from tomorrow onwards?
Okay.
And what I'm comparing to is what if you're just doing the optimal from today onwards?
Oh, so then it's the optimal would be computed from t up to capital T. Or maybe
yes, exactly. So at each time t, I'm recomputing the optimal for the future. And then I'm saying if I force you to take an action, what is the optimal value in the future for every sample path?
Okay, and the actions from 1 to small t, they're all given, is it?
The actions are just accept or reject in this problem. But the more general one would be the probability, like I can replace this with the probability we regret taking action A.
Yeah, but does the history matter? The choices I made earlier?
No, it doesn't. And that's very subtle. But for this policy, it doesn't matter. And in fact, that's critical. Yeah, that's a great question. So I'm somehow completely forgetting what happened in the past. In some sense, the past is represented through the current state. Okay, but so I don't care.
That's like the Markov property in some. Yeah.
That is kind of like the Markov property, but this is going to come back when I talk about the coupling argument. So this is basically this argument that mistakes I've made in the past have already paid for them in a certain sense. But I'll make that formal. That's a very, very good question. So it's subtle here that I don't care about actions I've taken in the past, except in the budget.
Okay, all right. Okay, thank you. Please go ahead.
Yeah, no, that's a great question. So, okay, in case you're not sort of convinced about this, let me show you some variants of this theorem. So it's actually a meta principle over here. So for example, if you tell me that you have predictors which, so the thing I showed you is it's a predictor based on like a LP relaxation. So anyone in control theory, what I really showed you was using the certainty equivalent control policy at each round and then reiterating that. But you can do things like you can use predictors, some other predictor which has like some kind of summable additive errors, or you can use sort of other versions of this. So there are a very large class of algorithms, all of which have constant regret. And in that sense, it's kind of surprising this wasn't known. And I also this result can work even if you have like time varying arrival processes, correlated processes, discounted rewards in a much larger sort of set of settings. And what I was showing here is it actually works extremely well in practice. So this is the result for online packing. You can see that it genuinely is constant regret, and the regret is extremely small, and it's also very low variance. So in practice, this is a very, like, it's a very simple policy, but it's actually incredibly strong compared to the state of the art. There's the same thing for my generalized assignment problem, this payment routing thing. Now I'm plotting this in log plots. So these are increasing linearly in the log plot. So it's sort of a polynomial growth, whereas this is basically sort of becoming constant in the log plot. And then the same thing for bin packing. You can see that existing like state-of-the-art policies for this were all getting some kind of polynomial growth in the total, in the regret compared to the hindsight, whereas we are really just still getting a constant. So the short story being these algorithms work incredibly well. They also work extremely well if you didn't know the distribution. So some of you may worry that maybe all of this is because that I assumed we knew these PITs exactly, and I kind of used that in the problem. But it actually turns out that if you, for example, assume that your arrivals are IID and just use the plug-in distribution. So you take all the samples that you've got to now, construct the empirical distribution, plug it into our construction, you'll still get constant regret. The one case where you don't get constant regret is if you need to explode as well. So for example, if you get censored feedback, if you have to sell an item to actually learn its value, then you don't get constant, but you still get log T regret. So effectively pretty good. And there's a even more amazing thing, which is that you may not want to assume anything is IID. I mean, I think IID is a terrible assumption for anything in real life, but what's often true is that you have traces. So you know the exogenous arrivals from yesterday, which you can use for today's process. And it turns out you can just take yesterday's process as a proxy for today's arrivals and just use that to construct your predictors. And you still get constant regret using as low as a single trace. And I mean, to kind of show you how this looks, here what we are doing is we are looking at online packing. Forget about all of these other plots. People for this problem have optimal competitive algorithms, but a competitive algorithm has regret, which is growing linearly in T. Whereas what we're using is just one trace of data. So we have some complicated arrival process. It's a Markov modulated arrival process. We generate one sample path from the previous day and use it to feed in to today's process. And under very mild assumptions, we still get constant regret. So this class of policies seems to work extremely well under very, very mild conditions. So there's something magical about this idea of like taking a predictor and then doing the thresholding, which gets you these very strong results. Okay, so I'm going to skip this, but in the remaining 10 minutes, let me tell you a little bit about just the proof and the ideas underneath all of this. But before that, any questions about what the results are? So if at this point, if all I've managed to do is convince you these results are sort of interesting and you want to read the papers, that's already a win. So I do want to convince you, or does anyone have any concerns about what I'm showing in all of these plots? Okay, if not, let me give you a bit of a sense of how we ended up proving this, and then also like maybe a question that some of you should be thinking of, at least which occurred to us, was these are really well-studied problems why the hell was this not known? Like, why wasn't it known that there are these really simple policies which get these results? In particular, what people were looking at are things like these randomized admission policies, and they were always getting square root t regret. What was sort of the barrier in breaking through from the square root t to the constant? And it turns out, and this is very closely related to Joy's question, most analysis that you'll ever read for online decision problems, so if you read, for example, say a bandit policy or a competitive ratio policy, there's always this notion of you fix a policy in hindsight, which is optimal. And then over the entire sample path, you account for all the mistakes that you've made. So some of the past mistakes also matter because they sort of relate to like things that you do later on. Whereas what we are doing in this problem is we are always updating the benchmark. So as time keeps going on, I'm saying let's forget about everything that's happened in the past. Let's restart the problem from the current step and think about the optimal that we could have got from now till the future. So that's the first sort of main thing. I'm using a benchmark, and in particular, I'm using, like when I'm saying I'm using a benchmark policy, this is actually a shifting benchmark. So it's a benchmark which continuously keeps moving as I go along my sample path. And the only sort of really general tool I know for dealing with these kind of shifting benchmarks is to use some kind of a coupling policy. Now, if some of you, I'm hoping, have seen sort of stochastic coupling arguments. If you haven't, I'll try to simplify and explain what's going on. But I mean, at the heart of what I'm going to tell you now is essentially just a very simple sample path coupling argument. And then the point is, once you do the coupling, you get a formula for what the regret is, and then you can use your sort of standard like concentration of measures and like sensitivity and things like that to bound it. So what exactly is the compensated coupling? So the high level idea is as follows. So I have a benchmark policy. So in this case, the benchmark is what is the optimal policy in hindsight doing? So the optimal policy which knows the entire sample path. And what I'm showing here is maybe what the optimal policy is doing. That's this red policy, the offline, is it's not accepting these people. And then at time t1, it's accepting that arrival. So its budget goes down. It's not accepting anything. At time t2, the next arrival, it accepts the next arrival, its budget goes down, and this sort of keeps. So its state is changing at these points t1, t2, t3. And these points are different for every sample path. So for every sample path, there's a different point at which it changes its, like, updates its state. I don't know this red policy because this red policy is aware of the future. I'm running this blue policy. So the blue policy is doing exactly the same thing as the red, just coincidentally, until this time t1, at which point it doesn't want to accept the current arrival, even though the red policy wants to accept. So this is the first time the two policies are separating. And what I'm going to do is at this point, I will force the red policy to take the same action as the blue policy. Now, at this instant, the red policy, this offline policy, is kind of unhappy about this. It really wanted to accept, and I forced it to reject. And what I need to do is that I need to, whenever this happens, I need to compute some kind of extra compensation that I give the red policy so that its value remains preserved. So essentially what the red policy is doing is, at this point, it is switching over to playing a suboptimal action. But in order to preserve its value, I pay a compensation. And it is then sort of redesigning what it's going to do from this point onwards. So because I'm playing the wrong action, it's somehow changing everything that's happening in the future. So the benchmark has completely shifted in the future, but whatever loss I incurred was incorporated in this compensation. And then this keeps going on. At this point, the blue policy is doing something the red policy is not doing. I will force it to change. Again, the future sample path will change, etc., etc. So like this offline policy keeps on changing every time the two policies disagree. But what's going to happen at the end is you can kind of say that like throughout the time, the state space of the two, the online and the offline policies remains exactly the same. And the way I'm achieving that is by computing these kind of amortized costs that every time I force a change in the offline policy. So that's why this is a coupling. I've sort of taken a random offline policy and some online policy which I'm aware of because I've designed that algorithm, whatever it is. And I've forced the offline policy to sort of couple together with the online policy on each sample. So they have exactly the same sequence of states, but in order to make sure that the offline is still offline, I'm computing the difference in the process. So let me make this a little more formal. So let's again just think about online packing. So I'm at some time t, and I have some budget bt, and this was exactly what Joy was asking, that at this point, what about all the things that happen in the future? I'm going to completely forget about those. So whatever has happened in the future has happened. Let me think about the offline policy starting now and with budget bt. And I'm going to define what I'll call a disagreement set, which is a set of sample parts from now till the future, where taking action A is suboptimal. So starting from now, if I take action A, this is suboptimal for that sample part. So this is some random set of sample parts for every action A. And here's kind of the compensation in math. So what I'm claiming is that the offline is getting the maximum reward today that it could with the current state and the current budget. This reward is less than equal to whatever the algorithm gets, because I'm forcing offline to take the same action as online. Plus, I may need to compensate it whenever this action was suboptimal, but the compensation that I give is at most the maximum value. So if I force offline to accept something which it didn't want to accept, it may be forced to reject something in the future, but the difference is at most the maximum value. And at this point, offline is going to resume the problem from the next time period, but its state is exactly the same as the algorithm. So this is same as alg. And I can now sort of repeat this process, and by just telescoping, what's going to happen is this is going to cancel out with the next day and so on and so forth. You'll add up all the rewards, which gets you the total value that the algorithm is getting. On the left-hand side, when you add up, you sort of get the initial value that the offline solution had. And the difference is going to be the sum of these compensations. But the compensations are basically Vmax times the probability that at each time you took an action which was the wrong action. And remember what the base selector was doing was it was exactly picking the action which minimized this probability of causing regret in hindsight. Now, this is subtle because I'm not claiming this is optimal. It's actually not optimal. That would violate the Bellman equality, so the principle of optimality for DPs. But this is still a valid upper bound for any algorithm. So for any algorithm, if I can estimate this QT of AT, where AT is the action that the algorithm took at time t, if I could bound this and add them up, I would get the total regret. Now, I still haven't finished this because I need to somehow tell you how to bound this. But in principle, at this point, when you have a decomposition of this sort, now it becomes a much easier problem. So now you can use sort of standard like concentration tools in order to bound these probabilities. So this really is the magic in what's going on. So maybe I'm going to do a long dramatic pause to see if there are questions.
So can you replace this Vmax with also some kind of expected term, like in particular?
Yeah. No, that's a great question. So yes, you can. So one thing that you could do is you could replace this. So more generally, instead of having Vmax, I don't know if I'm talking about this, but I could replace this whole thing with the difference of these two. So
right.
in anyone who does any reinforcement learning, this is sometimes called the advantage function. And you can replace it with a version of what's called, so yeah, the short answer would be yes, you can get much more refined versions of it. For all the results I showed you, this is enough, but there are actually more complex settings where you do need to replace this with something more exact. So exactly what you're thinking about, I guess, that if you have a state space which is infinite, but still the probabilities tail off, then also this would work by replacing it. Yeah, that's a great question. Jai, you had a question.
I was trying to get some intuition. So here the thing is, every time you take a wrong action, there is this compensation that is being paid to the offline policy. Now,
yeah.
Then over time,
yes.
why doesn't the compensation grow? And How does it
Okay, so
constant?
that's a great question. I'm not going to actually show you that. So let me flash an outline which suggests what's going on, and then let me try to explain it intuitively. So for the particular case that I showed with these exchangeable actions, the main thing on the slide is, okay, this is still the same thing. I'm sort of writing down the compensation. What I'm claiming is that there's at least one action for which the probability of making an error is exponentially decaying in T. And at this point, you can kind of see if I substitute this e to the minus t into this, if this is like e to the minus t, and I times some constant and I sum it up, this is some constant.
Oh.
Now, what exactly is going on? So let me sort of give you an intuition. So what's really happening is, suppose there were multiple actions at any time. What I'm claiming is there's either an action which is really important that you take it. Like it is clearly the right action that you should take right now, in which case a predictor will very easily be able to detect it. Like you must do this. You must accept the 100 in the initial case, or you must accept a 50 if your budget is equal to the remaining horizon. On the other hand, there may be other cases where there are multiple actions which look equally good. It's like, yeah, it's okay if you accept, it's okay if you don't accept. On like half plus delta sample paths, accepting is a good idea. On the other half minus delta, it's not a good idea. But whenever that happens, it actually doesn't matter which action you take at a very high level. So I'm not, now, of course, I'm missing out something there, which is like, how small is this delta? And what I'm claiming is the good and bad actions separate out very sharply as long as there's any kind of regularity in your underlying process. So at each time, there is one obvious good action and everything else is not good. Or there are multiple good actions, but they're all good enough and it doesn't matter which one you take. But sort of formally, there's always one action which has exponentially small probability that you regret it in hindsight. And I mean, this requires, like, this is the heart of the whole thing. Like this is not trivial to show, but it turns out under like sort of these mild assumptions, you can just use some concentration arguments to show that.
Okay, and the policy that you mentioned, the one that I don't remember what you called it. The one that
the base selective, yeah. So it's always picking that action.
Okay, it is picking this action which is highlighted here. Oh.
Yeah, so I'm somehow identifying an action which has a low probability of regret in hindsight, and then just going with that. It may not be the optimal action, but it's a decent action with high probability.
Okay.
So the critical thing is that for every state uniformly, such an action always exists. And that's not at all obvious. Like, so I think in terms of technique, the coupling is more important, but like in terms of like what's non-trivial, like doing that calculation is actually somewhat non-trivial.
Oh, thank you. Excellent.
Okay. Can I take like maybe 2 more minutes? I know I'm a few minutes over time.
Yes, please go ahead.
Okay, thank you. So that's sort of my very quick overview of what's going on. I mean, if you all want more details, so I'll actually send these slides over as soon as I finish. I've tried to write this down in a little more formal way just to show you exactly what's going on. But like once you get the idea of searching for this coupling, it's almost obvious. It writes itself, and like the decomposition is almost obvious. But it's not a priori. Like somehow all the analysis before this was not using this kind of simple idea, or like very few papers were using this kind of a decomposition. So let me kind of just briefly conclude to tell you where all or what all I've talked about. So essentially what I was talking about was this notion of like using these simple algorithms, which use these predictors for doing online decision making. And I gave you this way of using the compensated coupling to get these bounds. But this is in some sense really a tip of the iceberg. So you'll already identified a bunch of assumptions which I had which wouldn't extend. So for example, someone was asking about what happens if the jobs leave in online decision making, or kind of more generally, what if I relax the part about the exchangeable actions, or but there are actually many other assumptions I made. So I did assume it's a finite horizon. So what if happens if I switch over to an average cost problem. So a problem where in steady state, I want to sort of still get good results. And or what happens if you look at discounted problems or various other aspects of this. And this is something we've been like exploring since what I talked about. So for example, we do know that under discounting, there are problems. And in some sense, it makes it questionable as to why discounting is a good way of modeling MDPs. Like people use discounting to more because they think it's lower complexity, but it actually turns out that it makes the regret much worse. We've also been thinking about connections with kind of multi-objective settings, in particular fairness. I know this is something that people here who are really interested in. Like Sid has some amazing work, the other Sid, on like thinking about fairness in adversarial settings, but like in practice, and this was some work we were doing with the local food bank, when you want to think about online fair allocation, you still want to do much better, and you want to kind of use the stochastic assumptions and do as well as you can. Maybe a more higher level plug is like my work sits right in between like these theoretical cases where you want to think about worst case models, and then in practice where maybe you have some regularity, and it's often not enough to just define an algorithm in one case. You usually want to understand the whole space of like, there are cases where worst case models make sense. There are other cases where stochastic models make sense. And somehow people kind of use the wrong results or the wrong algorithm from one place in the other place. And in practice, this causes, I mean, it's suboptimal in many ways. So one problem I do feel that is there in this whole area is that even to study these problems and understand what other people have done, it's tricky to do comparisons because people make such very, very different assumptions, or they model the problems in very different ways. And then it's tough to actually compare against what other algorithms are doing. And one of the things we've been doing as a side project is like based on like these results is that we've been trying to make benchmarks for many of the problems that we really care about, so that everyone can take their algorithms and compare them on a common framework. And this is like an idea which has been very prevalent in like modern machine learning and modern reinforcement learning. And really what we've done is we've spun off some of these RL benchmarks and sort of incorporated like problems that we would care about more in real life. So things like more stylized things like multi-am bandits, but sort of more real life problems in operations research, or things like ambulance routing or revenue management, or in my case, I do a lot of work on ride sharing and or vaccine allocation, or problems of that sort, where these are very large MDPs, but we write out all the backend simulator, and we also implement like the best algorithms that we know of. And then what we're hoping is people take this, and like whenever you are trying to work on these problems and do something new, you try to benchmark against what is known. So it's not that a worst case algorithm is not a good idea. It may be good in some settings, but it's good to, you shouldn't sort of just write it without comparing it to anything else. And we just want to simplify the process of comparing. So if any of you are interested, or if any of you are working on these problems and want to sort of help out in benchmarking these, this is entirely online on GitHub. So you should go check it out, fork it, tell us if you want to collaborate on this. I'll be very excited to talk about any of this stuff. And also more generally, this whole area of trying to understand the right underlying model primitives, so the right assumptions which lead to the particular regret results. This is a much broader question, and we're actually organizing a semester on this at the Simons Institute to try and see various ways of modeling this problem, and then how different communities look at it, and what are the different approaches which are used. So a lot of these talks, or all of these talks, will be online. So I'm hoping many of you, so this is going to be next year in fall, so starting next September, and I'm hoping many of you also participate in that. One last note, so most of this work was done, I mean, some of you would know about like the way funding works in the US and about the NSF, and a lot of us, I know many of us who who have experienced the US academic system, many of us got our funding from the NSF, and especially under the control directorate, since a lot of us worked in control. And perhaps the most important person in controls in like the last 20 years was this gentleman here, Dr. Kishan Baheti, who was the sort of head of the controls directorate at the NSF. And unfortunately, so a lot of the inspiration for this work was based on like direct conversations I had with Kishan, but unfortunately he got COVID a few months back and actually passed away. So yeah, I mean, I wish I could get to talk to him, but hey, I think he would have wanted me to talk to all of you all, and hopefully you all can take this on. So thanks to Kishan for everything he's done for our community. And okay, with that, I'm done. Sorry for running late. But I'm free to stick around if you have any questions.
Thank you, Professor Siddhartha, for an informative talk. We can take a few questions now.
Hey, Sid, so I guess like it's robust to noise in your distribution as well. Like the coupling term would have a noise thing, and that will just kind of pop out, or
great.
more.
So, yeah, good. So what's happening is actually exactly that. So in some sense, the reason we are getting the robustness is, the way I like to think about it is, what couplings are very good at doing is they're very good at finding natural cancellations in stochastic processes. So at each time, if I think about what it needs, what has to happen in the future to throw me off, the noise is actually pretty significant. And so for this probability of error to become small, like the noise has to be quite significant. So maybe another way of saying it is, even if I take this and add some like delta t noise, I just need that delta t to be summable. So if delta t is something like 1 over t squared, then also you're fine, because you can just add that up and get constant regret. There's not a great answer because I'm not sort of formally proving it. I mean, okay, we've proved some formal versions of like the robustness, but the intuition and this is in some sense the magic of couplings is they just find these like destructive or like constructive interference in some sense. You get a lot of automatic cancellations and you only get like what is critical in the noise. But no, that's a great question.
And so yeah, one more like maybe a technical digression, but so like the other sort of variants of it, like the secretary problems and such, they have looked at more complex, so beyond packing constraints. So let's say it's not a knapsack, but let's say a more complicated combinatorial selection thing, like metroidal or something that fancies people like me. So
that's why I'm actually stating it this way. All of that I think would work. And really what we need is this function. So I was saying that you have this function in hindsight, which is which only depends on the aggregate state action counts. We need that function to be Lipschitz. So this is true for things like matroid. So I think there's a sort of hidden question there, which is like why are secretary bounds so much worse? What they are really doing, and the reason for the bounds being worse, is that the distribution. I don't know where I've stated this, but in some sense, the critical thing that I'm assuming is that I have a finite set of arrivals or a finite set of arriving types, and these distributions are independent of so this part where I'm saying mild bounds on the arrival process. What I really need is that these PITs or these probabilities are independent of t. So, and I don't mean independent in a formal sense. It's just like I fix the probabilities and then I scale t. Whereas all the worst case bounds jointly scale the probability and t.
Right.
So maybe one version of this is like in bandits, we kind of know that if you have what's called a gap between the best term and the second best term, then the regret is like log t over like this gap.
Capital delta,
Yeah, exactly. But if that gap goes down to 0, then the regret becomes square root t.
Right. Okay.
So this is similar to like a gap dependence for MDPs in that sense.
Okay. Makes sense. Yeah. Thanks.
Oh, sure. Yeah. Rahul, you had a question.
Any intuition as to why randomization is a bad idea here?
Yeah. So maybe I'll give you a silly answer first, and then so the silly answer I was thinking of giving is, if you imagine in like this puzzle that I gave all the way in the beginning, it's kind of clear that randomization is terrible here, right? Like I definitely should accept the 100. If I ever randomize on 100 before I hit the stopping time, I may not be able to make up that error in hindsight? So this is almost a silly answer, but I'm basically saying it's very easy to construct examples where it was clear what the right action was, but if you sort of randomized on that, you may not get a recourse in the future. Now, formally, what's really happening when you randomize is when you look at this kind of a coupling term. Where do we? So if you think about this probability of making an error, for example, when you randomize, you're adding another extra randomness, so some epsilon t. And typically the amount of randomness that you add, so one thing people often do is they take that probability, the xt, and then they randomize using that xt. So I was saying take the xt and then threshold at 0.5. So either accept if that xt or this probability of regret is less than 0.5, else reject. If you take that probability and randomize using that, then the amount of noise you're adding is on the order of square root t. So this is a little more technical and you need to sort of work out the details, but like essentially randomization adds noise to the process, which is going to throw you off. Now, there is a hidden question here again, which is like, why have you read so many papers which do randomization? And there are kind of two answers to that. One of them is if the underlying process is actually adversarial, then randomization is necessary. So the one case where you have to randomize is if you're sort of formulating this as a zero-sum game, where there's an adversary who is deciding what these arrivals are, and you're using randomization to push the adversary off. So there's no deterministic process which would do well in that case, but the randomization essentially gets you the right result. That's the good answer. That's the answer that there are settings where the randomization is necessary when you don't have any regularity in the process. The not as good answer is that in many cases, if you randomize, it's often easier to analyze. So when people try to compare against the optimal policy in hindsight, like they fix a policy and compare against that, and then you have a randomized policy, what you can often show is that in expectation, your randomized policy has the same expectation as your hindsight process, and then you try to bound something else, like maybe what's the probability of budget overflow. But you're using the randomization to get things equal in expectation for a fixed benchmark, and that just makes the analysis easier, but there was no principled reason why you needed to do that. So often if you like see these papers where they suggest randomization, they won't actually tell you why they're doing it. They'll often be like, oh, now observe, we have the same expectation, and now we do some Chernoff walls.
Got it.
In a principled way, you should never randomize in an MDP. Like in an MDP, this is kind of one of the principles, like the core principles of Markov decision processes. The optimal policy is always deterministic. It is always play the action given by the Bellman equation.
I see. But if you have a multi-objective MDP or a constrained MDP, then you might need.
No, even in a constrained MDP, you never need to randomize. You always play the action which maximizes current reward plus the value to go. Even for multi-objective, it depends on how you define a multi-objective MDP. But so we've done some work on, for example, looking at fairness. If you pick a point of like how you're trading off the objectives, you still don't need to randomize. So like the only case where I know you fundamentally need to randomize is if your arrivals are adversaries. So if you're playing a zero-sum game with an adversary, but otherwise randomization is always just a tool to make it easier.
Got it. Thanks.
Other questions, thoughts? So, I mean, I will share these slides. As I said, I'm super happy to sort of talk more about this. I really wish I could be there in person. I was thinking I'd be there, but well.
Hey, so does it make sense to think about lower bounds in this framework? Like say a dependence on Vmax is unavoidable, or this dependence on
that's
email.
A good question. So that's really hard. So I'll show you one, maybe I'll flash one of my backup slides. So this is a result which we didn't know and then someone else found out. So everything I was doing was for a finite distribution. You could naturally ask me, what happens if I do knapsack with a continuous value? So unit demand knapsack, but I have a continuous distribution. In particular, what if I just have uniform 0, 1? That's like the simplest case you can think of. And there's a really nice result I mean, it actually turns out this result was known before, but using more complicated methods. But there's a beautiful result by Rob Bray at Northwestern, where he showed that you can use the coupling, the same compensated coupling, to show that you can get log t regret. Log t is actually tight.
Theta.
Yeah, exactly. So in this case, it's theta. Showing that lower bound is incredibly hard. So in general, lower bounds for these problems are hard. So that's why I was getting uniform and like sort of celebrating at this point, because it's like, hey, it's a constant. Like, what could be better than a constant? But no, I completely agree with you. So maybe a more concrete way of asking it this is, if I tell you there's some general distribution f, for like it's IID with some general distribution f. So for example, I was assuming it's the distribution is like it's VI with probability PI, and the bound I gave was something like Vmax times summation 1 over PI. Whereas this guy is giving this bound, it's log t times a constant. But in general, we are getting something like this. Like the more general question would be, what is the function? So there's some functional of the distribution, which is going to show up here. So something like maybe the entropy. I mean, it's not the entropy, but it's some more complicated object, which is something like this in the discrete case, and it's something like this in the continuous case. And we don't actually know what's the right answer. Like this is something, I mean, I'm sort of actively working on, but it seems like a hard question.
Right. Yeah. I mean, the stochastic, so much more, harder to prove lower bounds in forgiving environments.
Yeah. Yeah. I mean, and especially because this is an online process. So it's remarkable that we know these lower bounds for bandits, but like actually most people know that the lower bound is like whatever log t over KL divergence. Most people haven't actually gone through the proof. Like it's almost magical that came before all the excitement in bandits, like the proof of Lyon-Roberts for the lower bound. And it's subtle. Like it's a really beautiful information theoretic argument, which it's still perhaps it's definitely the least taught aspect of bandits because it's somehow the hardest. So yeah, like short version, lower bounds are amazing. I have huge respect for people who prove those, but yeah, they're hard.
And so, like, final pedantic question, then I'll keep quiet. So, so the typical proof of this profit, or this like the very foundational result of like Samuel Kahn is not through coupling. So, as a learning exercise, like, does it, if you use the same this compensation argument, do you recover that bound for the very basic?
Yeah, good question. So there is a very nice, it's almost a coupling argument. So there's a coupling, there's this argument by Kamesh Munagala. In fact, he has some tutorials online on this, where he basically shows this amortization argument, which gets, like you take the LP and then you do this really cool amortization, which shows you get the half competitive ratio in very general sense. So even though those proofs look different, the modern ways of doing it are definitely closely related, but there is a sense in which all of these worst case problems collapse to static problems. So I don't have a good way of saying it, but in some sense, in the min-max versions of these problems, it essentially, the state doesn't matter anymore. Like you can have a policy which is just state independent, and that's still good enough, or almost. So we don't understand this very well. Like we don't understand exactly what is happening. Like we understand worst case bounds pretty well, and we understand these kind of average case or like smoothed bounds pretty well. But what's happening at the boundary where one goes from average case to worst case is like, we don't have a unified way of handling that. And again, I keep mentioning bandits because that's the amazing thing with bandits, where the same algorithm, like UCB is optimal throughout the regime up to like constant. There's nothing even nothing even close to that for these, like something as simple as the knapsack. We don't know how to do that. Like we don't have a best of both worlds algorithm for knapsack, for example.
Okay.
Yeah, no, that's a great question. I don't think that was pedantic at all.
Thanks.
Preetam. Yeah, sure. Preetam, you had your hand up. Do you have a question? Anyone else? Or can you guys still hear me? Oh, okay, yeah, I can see you can hear me.
Pritam, you're mute. We cannot hear it.
In the threshold, oh, what's the significance to 0.5? Great question. It doesn't matter. It can be any constant. Maybe the reason I picked 0.5 was basically because they're just two actions. So in this problem, there were just the two actions were accept or reject. Now, this is very subtle, but these probabilities don't actually need to add up to, okay, I'll have to go pretty far back, but like the probabilities could be less than 0.5. So the probability of, there are cases where whether you accept or reject, you'll actually get, you're not going to regret in hindsight. But what you're always guaranteed is, sorry, I have to go. Yeah, so you're always guaranteed that the action with the lowest probability of causing regret is less than 0.5. And this is just like a pigeonhole argument. I mean, the sum of these probabilities is at most 1. So the smallest one must be less than 0.5. So I'm kind of simplifying it by saying just go with like 0.5. But maybe a better way of saying it is go with the action with that lowest probability. Like take the greedy action based on this predictor. But why I said it's a great question is, okay, now we're getting into the thing that I was mentioning to Sid, that we don't actually know an algorithm which is worst case optimal, but also gets you the good average case bounds. It's possible that a good algorithm is something like you do this thresholding at say 0.25, and between 0.25 and 0.75, you randomize. We don't know if that's actually not true. So that algorithm, which thresholds below 0.25, thresholds above 0.75, and randomizes in between, that also gets constant regret. So it's kind of this general theme of what I was saying. There are many algorithms which get constant regret. We don't know a way of saying one is better than the other. And it's quite possible that one of these is also good in the worst case sense. At the moment, our best guess is actually randomized, just thresholding right in between is the best, at least in simulations. But I mean, this is a really good question. And I mean, it's something that does keep me up at night. So yeah, thanks for asking that. Okay, if not, I sorely need some coffee. Given you guys are in Bangalore, I'm hoping you will somewhat appreciate that. So thank you very much. As I said again, I wish I was there in person. Really enjoy visiting, but yeah, fingers crossed next year in IISc, hopefully.
Thank you again, Professor Siddhartha. As discussed before, I'd like to remind the audience to subscribe to our Google Groups, which is the mailing list on information for future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will also be posted on the webpage. Thank you and have a great evening.